Hello, everyone. My name is Abdessalam OUALLALI, young researcher from Morocco in the Geology Department at the Faculty of Science of Tétouan, Abdelmalek Sadi University. I am very pleased to be here with you, very happy to participate in this conference and especially to test this experience of making remote presentations. For this, I warmly thank the entire team and the entire organizing committee for this international event, which was able to bring together researchers from around the world. I would also like to thank the scientific committee and all those who contributed to the success of this event. My special gratitude goes to Professor Velibor SPALEVIC, with whom I have collaborated several times and who has shown a spirit of good research who helps young researchers from around the world. So my contribution relates to a part of my research work under the title Application of INTERO Model for Studying Soil Erosion Processes and Peak Discharge in the Western Rift of Morocco, north of Africa. So I start my presentation with a bibliographic review that we carried out in the Moroccan Rift. So water erosion is a phenomenon of both natural and anthropogenic origin, which affect the soil and liturgical formations. The driving factors of erosion are multiple. We can cite anthropogenic activity, overgrazing, fires, bad agricultural practices, degraded soils, degraded vegetation cover, steep slopes, and tectonic activity. The consequences of erosion are false in areas of erosion like low water retention, low infiltration and drainage, bad condition of pedogenesis. In sedimentation zones, we can observe deposition in insoluble places, low retention of dams, floods, and water contaminations. Morocco is not immune from the harmful of erosion, which increases over time. There are an increase in soil degradation. The sediment which moves downstream is more and more enormous. Loss of organic matter and mineral matter from soils, and a loss of storage capacity of dams. An example was made in the Tlata Basin, where the soil loses 14 kilograms of nitrogen, 16 kilograms of phosphorus, and 20 kilograms of potassium. The second example concerns water resources. The following table shows the state of large Moroccan dams. It can easily be observed that the dams of the Rift area are the most threatened since they show the highest values of siltation. So, Moroccan institutions have realized that they must intervene to keep and protect water and soil resources. However, the first essential steps to determine the sediment source areas and the areas at high risk of erosion. There are several methods and models that we have inventoried and which can be used. We have made a classification of these methods according to the expected results. There are qualitative methods based on expertise, empirical models that allows quantitative study, hydrological simulations, techniques based on radioactive elements, magnetic tracers, and finally, bathymetric measurement. However, anti-erosion interventions must be quick, so the study of erosion must also be done in a short time. To this is added the limits presented by the various methods. For example, radioactive methods are valid for studying short-term erosion. The revised soil laws equation and modified soil laws equation does not take into account forms of linear erosion, such as ravines, mass movements, and others. For these reasons, we thought of a method that has never been adapted to the Moroccan environmental conditions and will be validated and compared with realities on the ground using the measures of magnetic susceptibility. We are talking here about the potential erosion method, since it recognizes sheet erosion and forms of erosion, and it takes into account the lithological nature of the substrate and the type of soils. So the objective of our work is firstly to appreciate the methods already proven in various places of the Moroccan territory. This is why we have already applied the revised soil laws equation model to our study area, and its result will be compared with that of this study. The second main objective consists to apply new approaches as a first adaptation to the environmental Moroccan conditions, especially the environmental conditions of the rive. We are talking here about the potential erosion methods, which will be integrated in the INTERO algorithm. Finally, our result must be compared and validated by measurement in the ground. We will use the technique of magnetic susceptibility, which seems to us the most adequate and the most used in the current researches for erosion. The UPM method is a multiplicative function of several parameters related to temperature, rainfall, basin area. The parameter X depends on land use, pedological and lithological characteristics of the catchment, and the degree of extension of forms of erosion. Average annual sediment production must be multiplied by the percentage of sediment that reach the outlet. The following table illustrates the margins of variation of parameters taken into account by the applied model. With the INTERO model, it is much easier to integrate the data necessary for application of the UPM. The INTERO is an upgraded version of the river basins and surface and distance measuring programs. It is simple in handling and can be used to calculate a large data with the processing of 20 input numbers received after the processing of 26 result parameters. These parameters are summarized in the following table. So the choice of the area studied is not arbitrary. It is an area that has never been studied and which will experience a development of infrastructure with the installation of a new dam downstream of the basin. It is an area where the population is based only on the income from agriculture and will be half protected and preserved. We start with the preparation of the database necessary for the application of the model. The climate data were restored from the meteorological station installed in the basin. The hydrogeological framework was studied only upstream of the basin, where they are exposed to sandstone. We have inventoried the existence of the groundwater perched in this area. However, the rest of the basin is made up of marls and clay, which amplify runoff and limits infiltration. Therefore, the absence of the deep aquifer in this area. With regards to the pedological data, we have developed the soil map of the basin, which shows the predominance of vertisoil and poorly evolved soils, while hydromorphic soils and calcium-magnesium soils are limited in the basin. About land cover data, we used geospatial remote sensing to process a Landsat satellite image in order to prepare the land use map. The basin is mainly occupied by cultivated land, followed by barrenland, forest, and dense reforestation are restricted in this area. The map of erosion forms is the most difficult to realize. It requires a mapping in situ on the ground with verification by remote sensing software. This type of data is also a strong point of the EPM method, since the other erosion models do not take into account the factors of erosion forms such as ravines, gullies, and landslides. Here are some examples of the forms of erosion that are mapped in the study area and that are taken into account by the method applied, like landslides, deep ravine in the study area, periodically flooded areas, badlands zones, and others. The last parameter which has been studied deeply in this work corresponds to the data relating to the lithology. This work of geologists was done in the field, given the absence of detailed data on lithology in the basin. It also lacks a geological map of the area. This is why we have detailed the different lithological formations, their stratigraphic successions, and the tectonic activity, which also participates in the generation of erosion forms. We have therefore prepared 5 stratigraphic sections in the basin, 1 upstream, 3 in the center, and 1 in the downstream. This part allows to better understand the mechanism of formation of different type of soils on the different type of substrate. Therefore, the center of the basin is mainly marly and clay with intercalation of limestone banks. The same interpretation is valid for the section 3 and 4. If we return to the section number 1, we can observe that the downstream part of the basin is mainly sandy, on which are developed soil with sandy and clayey texture. To the southeast, marl flanks limestone formations are exposed. We have the absence of soil formation on the majority of marls. The 2 formations are deposited on polite of the Tangianite. Going to the upstream of the basin, we only notice Numidian sandstone, which are fractured into blocks and which are deposited in trust sheets on polites of the higher Cretaceous age. This formation has a layer of soil developed under on all the reforestation in white pine. The first result of this study is summarized in this table. It shows the values obtained from the parameter Z for the entire basin. We have identified 5 classes with more than 18% belonging to the class greater than 1. The result of sediment production were represented in the form of a map expressed in ton per hectare per year. The values vary from less than 7 to more than 16 ton per hectare per year, with an average equal to 28 ton. The highest values are recorded in sub-basin 5 and 6. They coincide with the marls of the lower Eocene. The materials moved under are deposited in the river terraces of Sultanian Arabian age. Upstream of the basin is generally stable, except in some areas where there are landslides and fault of sandstone blocks. To highlight the effect of lithology and major erosion factors on sediment production, we performed an intersection between each erosion factor map and erosion rate map. This methodology allows to highlight the lithological formations that release more sediment by comparing the percentage of low and excessive classes of erosion for each type of lithological formation. This operation allows to distinguish two areas of sediment production and an area considered rather as a deposition or a sedimentation zone. In fact, the whitish marls of the lower Eocene release the greatest part of sediment. This formation is largely located, as we said before, in the sub-basin 5 and 7. This justifying the increase of sediment losses in the sub-basin 5 and 7. Field visits shows that this formation located mainly in the center of the watershed in the form of hills has high altitudes and it is completely devoid of vegetation. The lithology is variable with frequent tectonic activity, generally in form of normal faults with calcite crystallization. The second lithological formation favoring the production of sediment and release materials corresponds to the upper Cretaceous olivaceous clays of the Tangier Inite. In the quaternary pluvial formations, sediment production is very limited considering the combined effect of erosion factor state in this area. The observation of certain profiles belonging to this formation indicates that it was indeed a deposition zone, where the phenomenon of sedimentation and transport material is very frequent. About the effect of the slope, in the study area, slope classes 0 to 15% has a lower percentage of sediment production rather than the other classes of erosion. Areas with slopes that vary from 15 to 13% are most favorable to show erosion owing to the combined effect of this factor with the other parameters influencing the degree of production of sediment. This class of slope coincides with poorly evolved soils that are strongly erodible in the center and downstream of the basin. Regarding the form of erosion, unlike other forms, sheet erosion is the most dominant among the erosion patterns in the basin. It promotes more than 18% of sediment production. This huge amount of sediment produced on the areas with sheet and gully erosion causes adverse effects on the soil resources, especially since sheet erosion, as we know, is considered the most dangerous with regards to soil since it depletes them on nutrients. About the effect of land use, the maximum value were recorded on cropland with the predominance of the excessive class in sediment production, whereas the low classes attribute to only less than 8%. The minimum values were recorded successively under the land occupied by dense vegetation and under reforestation with a predominance of the class of low losses compared to the other classes. Our results obtained in this study are in good agreement with those obtained by other models applied in the basin, like the revised soil loss equation and modified soil loss equation and the model SWAT. This demonstrates the relativity of the applied method as can be seen in the following table. So The use of the INTERO model based on the UPM yielded relevant result on soil condition and sediment production. The average sediment production was 28 tons. The analysis of the results showed that the lower Eocene marlis formations are the most productive in terms of sediment that have been eroded and deposited in the quaternary fluvial terraces. Sediment mobilization in this study is mainly controlled by land use, lithology, and erosion forms. Slope and precipitation are also influence sediment production or erosion, soil erosion in general. The third conclusion, this study showed that the method applied can be used effectively to study erosion and assess sediment production under Moroccan environmental conditions. The validation of the result will be made using the magnetic susceptibility on 800 soil samples, which are taken on the basis of the resulting map of the INTERO model. Finally, I apologize for my language, my English. I wish that you can understand what I say, and thank you for your attention.